Welcome to one of our lessons today, and I'll be talking about the Poiseuille's flow, deriving it from Navier-Stokes equations. That's a well-known study of Poiseuille. If you're studying fluid mechanics, dynamics, and so on, you'll actually end up studying Poiseuille's equation and Navier-Stokes equations. Okay, so yeah, that's it. Let's start. Let's assume that we have a cylinder. Okay, let's say we have a cylinder here, like this, and that cylinder has a radius. Say, the radius r, has a longueur r, and yeah, that's it. And there's pressure. Okay, let's call it pressure. Let's get pressure 2. Okay, and the flow is going actually this way. Okay, and first of all, we have to understand the principle behind a flowing in a cylinder. Okay, so let's say the flow is just like this. That's a cylinder. Okay, and there's the flow. How will the speed profile be? How will the speed profile behavior be in this case? Let's say that we know that at this point here, okay, here at the wall, we have that boundary condition, the non-slip condition. Here we assume no, that's approximately 0, the speed of the flow, and here as well, and the maximum occurs where the radius is 0 here. So we have a profile something like this. Okay, yes, like this. Here is the u max. That's the maximum velocity. Here is 0, and at the let's say that's at the r, it's equal minus, say minus r, that says it's equal to 0, r is equal to r. We have 0 as well. Okay, and as well as before we go, we have to understand that we are working in cylindrical coordinates, and then if we are working on cylindrical coordinates, we have to some assumptions. We have to make some assumptions that will help us to have our equation easily calculated. And let me say that these assumptions are not assumptions to have the solution, are real assumptions that we are making here. Okay, so we are working in cylindrical coordinates, and then we have, instead of having like x, y, z, we're having here r, theta, z. So in this case, we will flow this going this way. So for us, this is z, let's say this is r, let's say this is theta. Okay, so r, and this is theta. We're working in cylindrical coordinates. Okay, then let's make our assumptions. So here let's call it assumptions. Let's say we are working in a Newtonian incompressible fluid. Newtonian incompressible fluid. So for example, can be water, can be other one, but in this case, most of the time we use water as a Newtonian incompressible fluid. Let's say the flow is axisymmetric. If it's axisymmetric, then we assume that all the derivative in the theta direction is equal to 0. And we assume as well that z constant. Okay, there's no and we're saying that all the derivation, partial derivation in z direction is equal to 0. I say the flow is uniform, or it's a stationary flow. We're saying that there's no change in time, which is equal to 0 as well. And that's our all assumptions here that will help us to calculate our Navier-Stokes equations. Okay, so if you say that, then we're saying that the speed, okay, which is in r theta z t, this should be equal, okay, the components of the vector, the speed is in vector, should be equal to vr, which should be in r theta z t. For us here is actually null. Okay, the second coordinate in theta should be r theta z t, and for us is the same thing, null. And the third coordinate z in speed v in z direction should be r theta z t. And for us here, what's null is just the 3 plus components, and we're assuming here that the speed it is in z direction, but depends on r. Okay, depends on r. And so it means that our equation, our speed theta z t is equal to v r in function of r in z direction. Okay, that's what we are looking for in the first part of this equation. So, and then we have Navier-Stokes equations, NS equations, plus continuity for cylindrical coordinates. Okay, continuity for cylindrical coordinates. Okay, so let's say our Navier-Stokes equation is actually this over t of v times, this one is of v t. Okay, sometimes I write like this, and plus v gradient v is equal to 1 minus mass density gradient of the pressure times mu, which is the kinematic viscosity divergence of the velocity. That's our Navier-Stokes NS equation, Navier-Stokes equation. Stokes equation, there are forces acting on them. As I said before, in previous videos, I actually showed forces acting in a fluid, and Navier-Stokes equation we have all of them. We have the viscous force. For us here is the viscous force. You can look up how this term appears in the previous videos on this channel. And we have a pressure force, this one, pressure force. We have inertia, which is the second law of Newton. Okay, inertia, which is the second law of Newton, and that's it. Okay, so let's say in cylindrical coordinates, okay, we have this. You don't need to memorize this. That's given. Mathematicians already calculated, and they show that the divergence of a velocity should in cylindrical coordinates should be given by this formula or this equation. Okay, which is r square plus 1 r plus 1 over theta plus z square. Okay, and from this we'll apply the two equations, the Navier-Stokes equation and the continuity equation. Okay, that's continuity equation. Navier-Stokes equation and continuity equation. We'll apply the continuity equation in the Navier-Stokes, most likely here, okay, and here, and we'll apply that continuity equation in Navier-Stokes for in all directions, in direction r of the radius, theta of the angle, and z, the direction which the flow flows. Okay, so let's see in r we have actually the partial derivative in r over time plus vr partial derivative of vr of r plus theta, so r partial derivative of er, so theta minus theta square r plus uz r z equal to minus p or r times, here what I did is just that I multiplied by let's see dynamic because I multiplied the Navier-Stokes equation. Okay, let's say I multiply this by the density. Okay, so if I multiply by density, this one here and here, I will have the dynamic viscosity. That one will disappear, and here at the left hand side, I'll have the multiplied by the density. Okay, so it means I have here rho, this rho dynamic viscosity, that's multiplied by let's say that's 1 over r 1 over r over r, so that's r times partial derivative, so we're here partial derivative of ur over r minus, it's close, minus vr r square plus or theta square minus 2 r square theta theta plus partial derivative, second partial derivative of ur over uz. Okay, that's in r direction, and we have to do the same in theta direction. We should give us theta, that will give us theta, so you say we have multiply here by the rho, don't forget, plus u r theta, so r times u theta, I mean partial derivative of r times v theta over r times partial derivative of v theta in the direction of theta plus uz partial derivative of u theta over z times times u theta over r, which should be equal to minus 1 over r partial derivative of the pressure in the theta direction times mu, which is the dynamic viscosity, that is 1 over r partial derivative over r of actually, let's say 1 r partial derivative of theta r times 1 r partial derivative of theta r times r minus velocity in the theta direction over r square plus 1 r square partial derivative of u theta, so theta square, that is plus again 2 over r square partial derivative of v theta partial in theta direction times 2 times it's the second partial derivative of u theta over in the z direction. Okay, So that is our in the our Navier-Stokes equation in the theta direction. The same thing happened here in the z direction. So we'll have theta partial derivative uz over u theta ut in the time plus that's u r uz partial derivative in the r direction plus u theta r times u z theta times u z z which should be equal to actually minus p z plus u 1 to r partial derivative. We say we write this here, and we have r z r times 1 r square u z over u theta square times second partial derivative of u z over z square. Okay, and we have all of our equations here. And what do we need to do now is actually apply our assumptions here, our assumptions to these, to annulate terms which we know that will be zero according to our assumptions here. Okay, and we're saying that the flow is stationary, so it means that one disappears. Okay, that one disappears. We're saying that there's no speed in the r direction, so everything that's is a ur disappears. So they disappear. Let me check. Okay, put this disappear. Then you can write here stationary. R is equal to 0. So disappears. Disappears. There's no, let's check here, disappears. That one disappears, there's a here disappears. That one as well. And that's it. And we are saying as well, everything that is axisymmetric, then the partial derivative of something over the theta in the theta direction or the angle also will disappear. So we are saying here that that one will disappear. Let's put another color. That one will disappear. Disappears. Disappears. There's no loss in theta direction, so it disappears. That one disappears. Okay, let's look our assumptions. Theta direction, that disappears. With theta is 0, disappears. Z in the z direction does not exist, disappears. And z in z direction does not exist, disappears. Theta direction here disappears. And let's say everything here disappears. And that's it. We actually all assumptions has been made here, and our equation becomes let's say becomes in the r okay, let's say in the r direction. It becomes actually partial derivative of the pressure over r is equal to 0. Say in the theta direction is actually the same thing, everything disappears. Okay, what's left in all of them here is this. Say there's this, what's left here is this, and what's left here is all of, let's say, this. Okay, that's actually what's left. And if we do so, that's equal to 0 in z direction. in z direction. Now z, what's left is partial derivative of the pressure over z direction equal to dynamic viscosity of 1 over r derivative of r partial derivative of uz in the r direction. Okay, r direction. So let's say what's left is actually this. So here we don't have pressure. Let's assume we know that as I showed you previous one, the pressure is acting here and here. That's pressure 1, pressure 2, and it's in z direction. Okay, so that is true, that is 0, and then of course that does not exist, can be a constant, but that constant does not depend even in r, z, or it's just a normal constant. Okay, so we assume that p depends of z. Okay, so and p1 is greater than p2, otherwise there's no flow in the pipe. So that's it. So if you look up at in the z direction at this expression here, we'll find that at the left hand side, see, at the left hand side, okay, here is z dependent, and here is r dependent. Okay, so that's simple to say. It means that for the pressure, all this term in the right hand side here is constant, and for the speed, all this term in the left hand side is a constant. So let's assume that the pressure over dz for us here is equal to a constant. Let's say a constant, let's call it g, that depends in z. We don't know yet if it's a normal constant or or it flows only in z direction, but we are saying that we assume that it's a constant. Okay, and then if it's a constant, that one will help us to the equation. And then we're assuming that g z equal dynamic viscosity, okay, 1 over r partial derivative over r of r uz u r. Okay, and if you do so, we do so, we'll have here actually z equal to 1 r okay, and I will have here gz r mu equal r. Okay, and let's say this equation will give me actually r z r. I'm integrating this term here. Okay, then if I integrate this term, I will have actually g z r square over 2 mu, okay, plus a constant a. Okay, and then u z u r, I'll have that one can actually be z r 2 plus a over r. Okay, and if I integrate the both sides again, I'll have u z r equal to g z r square over 4 mu times the integral of this should be a ln of r plus b. So that is our equation for the speed profile. And now we have to find these constants a and b. To find this constant, we have to apply the let's say boundary conditions. Okay, we're seeking A, B, which we don't know, so we apply boundary condition. Okay, so let's say to apply boundary conditions, we have to understand what's actually going on. I said before, our flow is in actually this. We're saying here is 0 and here is 0. So if we think is that if here is the r0, okay, if r is 0 with the maximum velocity, and we don't want this to be 0, we don't have this to be 0. If it is 0, then we'll have the finite, okay, finite infinite speed profile. If we have that infinite, we don't want this to happen. If we don't want this, then we assume no, we know that A for us, say A for us is equal to 0. Okay. And for B, we know that when R is equal to R, the speed R is equal to 0. So if you assume that, which is true through the boundary conditions, then I will have 0 equal to G Z R square for mu plus A0 0 plus B, and then my B is equal to GZ R square over minus GZ R square over 4 mu. Okay, for me that's my actually B, and from this my V profile, depending the speed profile should be given by, it says GZ GZ is R square over 4 mu minus GZ, that's actually capital R, okay, that's capital R, yes, and then R square over 4 mu, and V Z R is equal to G Z GZ 4 mu. So I'll have here actually R square minus that capital R square as well. So that is my speed profile of Poiseuille's flow. Okay, and then from this we can actually find the flow of it. We can understand, we can actually as well find the GZ. We know that it's a pressure we don't know yet if it is in a Z direction or it depends in Z. Okay, that one also we can find according to the equation, which I will do in a part 2 of this equation. Thank you.